Our first speaker today is Arlene Fiore from MI.
So hi, everyone. I am delighted to be here and to be part of this next round of HAQAST. And so today I'm going to give you mostly an overview of some of the questions that we're thinking about as part of our member projects, as Tracy introduced this morning. So basically one of the things that we're super excited about is what are we going to learn from TEMPO, which is this new geostationary satellite, the first time over North America that we're getting hourly information during daylight hours. And so this is just a loop of a single day that you're looking at from this horrific Palisades fire that happened earlier this year. My graduate student, Joe Palmo at MIT, has just put the TEMPO tropospheric column, nitrogen dioxide, and as well as formaldehyde here. And you can see that plume coming off the coast of Southern California, lining up with where the NOAA HMS smoke and fire data is showing smoke. And so you can kind of see that plume fanning out. Okay, so why am I showing you NO2 and formaldehyde for ozone? Well, just in case you're not familiar with ground level ozone, one of the challenges is it's not emitted directly, but of course forms photochemically in the atmosphere from a combination of reactive carbon species that we call volatile organic compounds, as well as nitrogen oxides in the presence of sunlight. And so NO2 is part of NOx, and formaldehyde is a nice proxy for VOCs. It is formed alongside ozone in the oxidation of those VOCs. And in the US, especially in the Eastern US, which is kind of our focus for our member project, in summertime when ozone is of most concern, biogenic emissions of VOCs are kind of the dominant, most highly reactive precursor for ozone with anthropogenic NOx. Okay, so for some of you who have been to prior HAQAST meetings, you've probably seen me or heard others in HAQAST talking about the role that formaldehyde and NO2 and this ratio between them can play for telling us about the sensitivity of local to regional ozone formation to VOCs or NOx. So we're kind of building on that work here, but tackling some new questions that are going to be challenging, but we're excited to see what we can learn. And so the first challenge is trying to understand what controls early season high ozone events. Our focus with our partners, NESCOM and New York State Department of Environmental Conservation, our stakeholder partners, is focused on this ozone transport region. And what you're looking at is the number of high ozone days in April, May, and June. So what are sort of thought of as early season events are shown in green, the green bar chart, and then the blue is the other events. And the percentage is shown on the right-hand axis as the green line. And you can see that percentage of early spring or early season, I should say, events is hovering about 50%. But if you look at the last couple of years, it sort of leads one to wonder, is there an uptick? Is something changing? And so 2024, of course, is an exciting period to focus in on because we have a full year of TEMPO data. But we're also interested to use satellites that have been flying back to the mid-90s to also place 2024 in a longer term context. And I should note that this work is led by postdoctoral researcher Madankwi Tao, or Tao Ma, who's at MIT. And so you're looking at just a calendar for 2024 for kind of the ozone season here. And you see that most of the early season events were happening late May and June. And the region that is of interest here where the high ozone is happening, and this is just a count of the number of high ozone days that each of the state and local monitors from April to June, you see that kind of eastern seaboard region light up there. So if she zooms in and now you're looking at the actual ozone concentrations on a specific day when one of these early season high ozone events happen, May 24th of 2024, you see ozone in that eastern sort of northeast corridor region above 70 ppb, maybe at some sites even a bit higher. And so now what I'm going to show you is a diurnal cycle of the tropospheric vertical column density of nitrogen dioxide measured or observed, retrieved from TEMPO. You're looking at 8:30 in the morning to 5:30 p.m. And what the spatial, the spread that you're seeing there is space. So it's all the pixels that Tempo is monitoring over this ozone transport region. And you see kind of what I think for those who are used to looking at diurnal profiles of NO2 is pretty much expected. You have higher vertical column densities in the morning and towards the late afternoon, evening. And what's interesting is on this particular day, Talma finds that that morning NO2 is 16% higher than the May 2024 mean, which possibly means that we have more NOx around to produce ozone, although there's more work that we need to do to really test that hypothesis. Interestingly, the meteorological conditions are kind of what you expect with a classic summertime photochemical ozone production. You have stagnant winds, high temperatures. So our working hypothesis is this is kind of a normal Eastern US event. But we're interested, like I said, to dig further and also explore other events, and especially the ones that happen really early in the season before the leaves are out and producing isoprene. I should mention that the formaldehyde was pretty similar to the monthly average on that day. The second challenge, which I sort of started to motivate in my title slide that we're interested in, is how much ozone do wildfires make? And of course, we care a lot about fires for PM and health, and ozone is really one of the questions that it's very complicated. It's not clear whether fires always make ozone, if they make it in transit, in which case ozone is potentially being transported in and part of the background, or whether the fires are bringing VOCs in that then mix with urban NOx, in which case my colleague and collaborator, Paul Miller at NESCOM says, well, then it's just like biogenic VOC and urban NOx, and it's controllable through urban NOx control. So the events that we're going to contrast here happened in 2023, so before Tempo was actually retrieving data, when these Canadian wildfire plumes hit not only New York City, but a lot of East Coast cities and really were captured in the news a lot. And what's exciting about having tropomi is that not only do we have NO2 and formaldehyde, but we also have carbon monoxide. And that's a nice tracer of smoke as well. And so we see that we have very high columns of tropomi CO over this kind of New York, Pennsylvania, New Jersey, Long Island Sound area on June 7th, whereas the CO as a measure of the smoke is more widespread, but still not nothing on June 29th. And what's really interesting is when you look at what's going on the ground from the state and local monitors, the muted contours are the PM 2.5 concentrations, and you see it getting up to purple, so very unhealthy over much of the region on June 7th and a little bit of the region on June 29th. And then the dots are the ozone measurements at the monitors. And what's intriguing is that we see that on June 7th, despite the super high PM and the high CO in the column, we see actually very low ozone on those days. In contrast, on June 29th, ozone levels are coincident with the high PM are also elevated and higher. And so what's different on these days? What are the conditions leading to this? These are the questions that we're trying to dig into. Okay, how now are we actually going to take a 2D column that we see from space and try to interpret it for what's actually going on where people are breathing? Actually, before I get there, I was just going to mention we're also excited about looking at other satellite products as well. And I want to call out another graduate student in my group, Steph Elkins, who is looking at peroxyacetyl nitrate data from the CRIS instrument. So peroxyacetyl nitrate is a reservoir species for NOx. And so we see elevated levels of PAN on June 7th, but not so much on June 29th. Chris is seeing the free troposphere, so there's a lot of work that needs to be done to connect what's going on to the surface. And how we're going to try to do that is by leveraging in situ airborne measurements to infer the chemistry and see whether we can come up with some generalizations to extend to satellite data where we don't have the in situ observations. And to do this, Joe is taking advantage of the FireX AQ campaign in 2019. I am running out of time, so I will just say that we're very excited about this. I'd love to talk to you if you're interested. Of course, we're also excited to extend to Tempo. In my less than a minute that I probably don't have left, I did want to highlight a new paper that was just submitted and is out as a preprint from Taoma, where she kind of stumbled upon something that I think is relevant for the Tempo and Trobomi and other satellites communities, which is that when she adds hourly emissions into a model as opposed to using a daily mean or a monthly mean for NOx, she finds that it actually changes the monthly mean average of not just surface NO2, but the vertical column density, which we think probably has implications for what you're inferring about emissions from space. So that's all I'm going to say. Some resources that are on the HAQAST website relevant for Tempo, if you're interested, and I will just stop there and acknowledge my team, my collaborators, the questions we're focused on for our member projects, and our collaborators. Thank you.
All right, thank you, Arlene. We're going to stay on the East Coast or Eastern US and move to Amanda Fritz now with the Connecticut Department of Energy and Environmental Protection.
There we go. Okay, hello everyone. I'm Amanda Fritz. I am an air quality forecaster from the state of Connecticut, and today I will be discussing the influence of upwind emissions and Long Island Sound on Connecticut's air quality. So to start off, here is our 2025 ozone season summary. We had 87 site exceedances across 22 exceedance days. Typically, our ozone season is from May 1st to September 30th, but this year was a little different. We had 2 early ozone exceedances in April on the 24th and 25th, and we even had an ozone exceedance on October 5th. There are some missing spots because on October 1st, we did start shutting down our ozone monitors for the season, so we did miss some crucial data there. We did have 4 days that had at least one site reaching unhealthy ozone levels. And another interesting thing is we saw the most number of site exceedances at Westport at 13, followed closely behind with Stratford at 12, and those are both Southwest Connecticut coastal sites. So then taking a look at the preliminary design values, I know it's a little difficult to see the numbers, but that darker shaded area is our New York, New Jersey, Connecticut non-attainment area, and our highest ozone design values there occurred at Westport and Stratford, and that was 80 parts per billion. And then the lighter shaded area is the greater Connecticut non-attainment area, and our highest ozone design values there was 73 parts per billion, and that occurred at East Hartford and Groton. And then I did include our trends on the right, and we have seen significant progress since the 1980s for ozone, but in the past decade we have seen more slowly decreasing design values. And I guess one of the main points here is Connecticut still remains in ozone non-attainment for both non-attainment areas for the 2015 standard, and then for New York, New Jersey, Connecticut non-attainment area for the 2008 standard. So then one main contributing factor to Connecticut's ozone problem is the impact from the NO2 plume over the New York City metro area. So because of this, we do like to keep an eye on trends, and we do use satellite data for that. So here I have the June, July, and August Tropomi data, and 2018 is on the left and 2024 is on the right, and we can see a little bit of a decrease from 2018 to 2024. But we also like to be aware of impacts to NO2 from control strategies. So one really great example of that is New York City congestion pricing. And we have been working with Dan Goldberg from George Washington University to help us analyze data on this. The latest data that we had available was spring 2025, and we have not seen a signal in Manhattan due to congestion pricing. There were some decreases, but those are well within any uncertainties. And we did briefly look at things at the end of summer, and we still really didn't see any impacts, but this is something we will continue to evaluate, hopefully in the near future. And then another significant impact to Connecticut's ozone problem with ozone forming near and in Connecticut is the impact from Long Island Sound. So at the most basic level, the PBL heights are higher over land than they are over the water. So for a typical summer day, we can see about 2,000 meters for those heights over the land. And then over the marine layer, it's less, it can be less than 100 meters. So basically for Connecticut, 3 of our main meteorological factors we look for when we're forecasting and analyzing ozone events are southwest winds, high temperatures, and sunny skies. So with regards to the southwest temperature, southwest winds, that can transport ozone from along the I-95 corridor in New York City, depending on the winds from downwind or upwind, excuse me. And then those pollutants, either the ozone that's already formed or the ozone precursors, get funneled over Long Island Sound. And then that ozone is forming, getting trapped in the shallow boundary layer. And then the sea breeze or the southwest winds are pushing those high ozone levels along the coast. So we can have many different scenarios that can cause either western only Connecticut site exceedances or across the whole state, or maybe just the coast, or maybe just inland. It all depends on what the winds are doing. So to show the impact from both the New York City NO2 plume and impacts from Long Island Sound, I do just have a few slides about one of our ozone events this year. So I chose July 16th because it is a primary example of ozone being formed near Connecticut. Typically, on other ozone exceedance days, we can see those high levels of ozone along the I-95 corridor, and that's ozone being transported into the state of Connecticut. But this is a really great example of that ozone forming. We had one site exceed, that was Danbury, at 75 parts per billion. And then we had many other states, particularly in Western Connecticut, that had ozone levels in the high moderate range. So then taking a look at PM 2.5, Connecticut did have good 24-hour PM 2.5 levels on this day, but there was a smoke plume to our north, and that's where all those moderate ozone levels, or excuse me, PM 2.5 levels are coming from. This is a very important slide if you kind of look at it frequently, so I'll just explain what it's showing. Basically, this is showing that all of our ozone sites were showing increasing ozone throughout the morning hours. Then our coastal sites are peaking between about noon and 3 p.m. And then we're also seeing our inland sites peaking later in the day. So, for example, Greenwich peaked the highest for all the coastal sites at about 2 p.m. at 87 parts per billion on this day. And then a few hours later, at 4 p.m., Danbury peaked the highest, which if you're not aware of it, Danbury is north of Greenwich. And then a few hours later at 6 p.m., Cornwall peaked at 80 parts per billion. So this is basically just showing that ozone forming over Long Island Sound and then being pushed inland from the sea breeze. So then, like I was mentioning earlier, main meteorological factors we look at are the warm temperatures, the sunny skies, and southwest winds. So in regards to temperatures on this day, we did reach the upper 80s into the low 90s across the state of Connecticut, with our highest levels or temperatures in central Connecticut. And we reached 93 degrees Fahrenheit at Bradley International Airport. And this is a typical day. If we see temperatures in the 90s, it definitely makes us more aware of potential ozone exceedances. And then we look at the satellite images to evaluate the cloud cover. So I really like the morning satellite imagery here because you can see that smoke plume to the north of us with sunny skies for Western Connecticut. And then later in the day, about 2 p.m., that's kind of when the ozone formation was kind of halting and it was more transport taking over. And we can see scattered skies across the state. And then one really useful application for tempo for us is the hourly tempo animations. And the main point here is on this day, you can kind of see where the sea breeze circulation impacts the NO2 plume because we see that moving northward. So the highest NO2 levels on this day did remain west of Connecticut, more over the New York lower Hudson River Valley area. But there was some of those high NO2 levels over the areas of Long Island Sound closest to New York City. So that's where that ozone was forming over Long Island Sound before it was pushed northward. And then another thing we like to look at, basically another way of showing it is the 24-hour back trajectories. So for this day, we looked at the HER back trajectories at 4 p.m. Danbury is that Western Connecticut site, and Groton is the Eastern Connecticut site. I chose this time in these sites, primarily Danbury, because that's when it peaked the highest for the hourly ozone, but also Groton to show that contrast between those monitor sites that are showing really high ozone levels versus the monitor sites that are showing lower ozone levels. So for Danbury, we're seeing, like you kind of can see with the tempo animation, those particles are traveling up the I-95 corridor over New York City, impacting a little bit of Long Island Sound before being pushed northward. Meanwhile, for Groton, we see more of an ocean influence, and those precursors and that ozone that was forming wasn't able to reach the eastern parts of Long Island, so there was cleaner air for that site. And then basically just some key takeaways: ozone remains an ozone non-attainment. And while the NO2 plume and Long Island Sound aren't the only reason that Connecticut is an ozone non-attainment, it's definitely a major impact to our sites. And we do look forward to doing more data analysis, especially with tempo, in the coming months. And hopefully we have something a little bit more in depth to show you. I would like to look more at emissions and see what emission sources are impacting that NO2 plume. Thank you.
And next up, we have Dan Anderson from the University of Maryland, Baltimore County, a HAQAST member.
Yeah, so excited to be here and excited to be part of HAQAST. So my first time being a HAQAST PI, I was telling Tracy that I was at one of the very first HAQAST meetings when I was in grad school at University of Maryland. And yeah, so I'm at University of Maryland, Baltimore County, but I sit at NASA Goddard. And because I'm not a civil servant, I could actually be here today. And so I'm going to be talking about the work that we're doing, trying to infer surface ozone using tempo and machine learning data, machine learning models. Just to motivate this a little bit, I think Arlene has done a good job pointing out some of this. Is, we're really interested in trying to understand ozone across the surface, across the United States. And we can do this multiple different ways, using observations, using models, using satellites, but each of these has their own limitations. So, if you have observations, they're great data, but if you don't live at a monitor, we don't know what the ozone is there. And those monitoring networks are very sparsely located. And if we have models, so this is an example from the NASA GSCF air quality model. So that's the Goddard model. And you can get broad spatial coverage, but you also often have significant biases. So that's what I'm showing here. I picked our model to show that we're not perfect. And then we have satellites. So satellites give you great spatial coverage. And in the case of tempo, you have very high spatial resolution and temporal coverage, but it only gives you information in the columns. So now is a great time to combine these various different aspects to try to understand surface ozone, because we have the launch of tempo that's giving us this really high spatial and temporal resolution data. And we've also had significant advances in modeling through machine learning, especially as they apply to atmospheric chemistry, that will let us go beyond some previous techniques that have been used to try to infer what's going on. So the goal of our project is to create two separate products. The first is a near real-time surface ozone product at hourly resolution that's derived from a combination of machine learning, satellite observations from tempo, and in situ observations. And then the second part is a short-term ozone forecast of the surface, something on the order of 12 to 24 hours that we build using a similar methodology. And the idea behind both of these products, but particularly for the forecast, is that it can be an additional tool for air quality managers to understand what's going on at their sites and to help with air quality forecasting. For example, one application is if you have an air quality episode where the emissions are very different from what the standard is. So something like wildfire events that may be difficult to model with an air quality model in real time because you don't have those emissions. Using our forecast that uses the tempo observations, the idea is that we would be able to maybe provide better information at much cheaper computational costs than something like an air quality model that uses data assimilation. So that's the hope there. And the idea is to provide both of these products at an hourly resolution across the tempo domain. That's very, in a perfect world, that's what will happen. We're starting this from the ground up right now, so we'll see what we get there. But I think some of the preliminary results that I'll show suggest that there's definitely regions of the country that I think we can be successful with this. And so because we are starting from the ground up, our near-term aim is really focusing on the product development and validation side of things. So making sure that the data that we generate is as accurate as possible and quantifying any uncertainties that we can. And so for the purposes of today, I'm going to be focused on this near real-time product because we're going to start with that, and that's going to lay the foundation for the forecast. And I should also point out there's plenty of other applications for this data in addition to helping with air quality forecasting. We have things like air quality model validation, product validation of other tempo products. So there's a near surface tempo ozone retrieval that's very experimental that we think there could be some good synergies with. And then also things like ozone exposure studies. So for the rest of the talk today, I'm going to show you some very preliminary data that we have for this work. And I just want to point out that the results are absolutely going to change. So the idea behind this is to just demonstrate some of the potential utility of the product. None of this is, set in stone. And before I get to that, I just want to point out our broader team. So in addition to myself, there's Brian Duncan, who's been involved with HAQAST since the beginning, I believe. And then we also have Kristen Okorn at NASA Ames, who's an expert in low-cost monitors, and then Gonzalo Gonzalez-Abad, who is very involved in the tempo retrievals. And then we have stakeholder representatives from multiple parts of the country. So WeStar, NESCOM, LADCO, and then Byung Kim from the Georgia Environmental Protection Division. So this is just meant to give you an idea of the sort of data that we're using to build our model. I'm not going to go into too many details here, but the general idea is that we have all of these observations at surface ozone monitoring sites from the EPA network. So we can take a subset of those observations and train a machine learning model on those observations to be able to predict ozone at those sites, and then apply that model more broadly. So those are the sites that I'm using for training at the moment. And on the left are the inputs that I'm using for my machine learning model. We have observations from tempo, so NO2, formaldehyde, and then also total column ozone, but also meteorological data that we get from meteorological reanalysis currently, and then also other data, things like population, day of the week, road density, things like that. So then we can then train our machine learning model at these sites and then apply it broadly. But the key here is the validation at sites that were not involved in the training. So if we can apply this model and prove that it works at other sites outside where it's trained on, that gives us much more confidence in its ability to work. And then again, for what I'm showing you today, this is just 2 months worth of data that I trained the model on, and I'm also using an older version of the tempo data that we will obviously update in the future when it becomes available. So this is showing a comparison of the observations at the EPA ozone sensor to the ozone from our tempo-derived product. And then the map is just showing the validation sites, which again are independent of what was used to train the model on. So this initial result at all of these sites for all hours of the day, I think is pretty encouraging. So we're doing a good job of capturing that variability. We do have, with very little bias, and we get our ozone accurate on average within about 5 ppb. You will notice that we do tend to underestimate the ozone at the highest values, which is unfortunate because that's where we're probably most interested in the ozone. That's not an unexpected problem. This is one of the issues with machine learning models. So we have some methods that we're looking into to try to improve this, including using more data should help fix that problem. We can also look at individual sites. So we can do the same sort of regression analysis at the various validation sites. So the figure on the left is showing the R-square value. So how good is that correlation for the data at the individual sites we're looking at? And so you can see in the Northeast and Mid-Atlantic, and we're actually doing a very good job at most of these sites. Our R-square is about 0.7 or higher. So we're able to get most of the variability in the ozone from this model. We are struggling. It's very clear, like as we go further west, that we are struggling somewhat. So that's obviously something we're looking into. And if we look at the biases, On the right side, we see again that for individual sites, our biases are generally within about 5 ppb, although we do have some sites, again, there's one in Southern California where the bias is more than 10 ppb. So trying to understand what it is about these particular sites that are giving us problems is one of the main things we're going to be focusing on in the near term. And then we can zoom in a little closer to one individual site for a time series. So she gave us a good look into what's going on in Connecticut. I apologize that this is very Northeast focused. We are looking at other parts of the country as well. But so this is that Westport site that she was talking about earlier. So you can see that there are plenty of days where we have very high ozone. And I was actually quite surprised at how well we're doing at this one particular site. So we're able to get, most of the variability. Our R-score is almost 0.9. There's some days where we are getting a lot of those maxima in ozone, but then there's other days where we're obviously missing a couple of the key, peaks. Even though we're seeing that it's peaking, we're missing that out. So I think one of the things that we need to do is look at these individual events to try to understand what's going on these particular days, so that we can figure out what's driving that. And we have some ideas. I think one of the problems I'm involved with right now, particularly at the site that has things like bay breezes, is I'm using a relatively coarse meteorological data sets, and I think that will not likely capture some of those issues. And then one other point that I wanted to point out before I wrap up is that currently we only have about 4 observations per day for our ozone product because of limitations with cloud coverage with like the tempo retrieval. So one of the things that we're really focused on is trying to figure out how we can sort of fill in those data gaps so we can turn this into something that's MDA8 ozone, something like that. So a metric that is potentially more useful for policy applications, even though, this isn't observations. And then I did just want to show this slide real quick, just to show that we're not doing great everywhere. So this Hackensack Beach site, which is just down the road, you would think we would have similar results, but we don't. And I think this is related to that meteorology issue that I talked about earlier. So, we are having, it's not perfect everywhere. So I'll just leave it there. I have some near-term goals up here, and then I'm happy to engage people from other organizations. I have my contact info here if you're interested. So thank you.
Our last speaker then is Angela Dickens from the Lake Michigan Air Directors Consortium, or LADCO.
Hi, everyone. Really glad to be here talking with you. And I'm actually not going to show any data or analysis from us, but I'm going to talk about some asks, some things we would love to see the community that we think would be really helpful. So just to give some background into who we are the Lake Michigan Air Directors Consortium. And we were formed in 1989 to bring the Great Lakes states together to work on air pollution, specifically ozone. But we do work with other things. So we're governed by the state air agency directors of the 6 states, all are kind of Great Lakes states. So we really do work for the states, and we do do a number of things. One thing we do is we bring the states together to talk to each other. So the states talk to each other mostly through our kind of work groups or our planning meetings. The most relevant thing for this meeting is that we do a lot of analysis. We do modeling for the states, photochemical modeling, data science, which is what I do, including some work with satellites. That's kind of where we how we connect to HAQAST. And we also facilitate training for the states. This is kind of the status of for our state areas for ozone right now, non-attainment. You see, we have a lot of the pink areas are non-attainment. We see there's a lot of non-attainment areas around Lake Michigan, very similar issues to what Connecticut has with the lake. St. Louis, where we are now, Cleveland, and then we have a number of other areas that were non-attainment and are now redesignated to maintenance, which is the ones with the lines. But what we're looking at right now is that those 4 areas all have redesignation requests in process. I think most of them, they're all out for public comment right now. And it's particularly given this, they're good packages, they're valid, but the CPA is also very eager to redesignate places. So we anticipate that very soon, all of our non-attainment areas are going to be around Lake Michigan, which is kind of the situation we've been in for decades too. So familiar situation, but we're really kind of shrinking the area that we're going to be thinking about to the area around Lake Michigan. In which case, the Chicago area is really the main story and when it comes to ozone precursor emissions. Really, the talk in Milwaukee, we heard if you were in the session earlier, someone was talking about like, wow, look at Tempo shows so much emissions from Chicago coming up to Milwaukee. Milwaukee obviously has a lot of emissions too, but like Chicago is really the main source. And if you think about Chicago ozone, you really end up having to think about VOCs. Chicago is one of the few remaining areas of the country that has a lot of evidence of VOC limitation. Lots and lots of different studies, including some work I've done at LADCO. This is a recent study by Zhang and Jin at Rutgers looking at Tempo formaldehyde NO2 ratios and finding, she actually found the most VOC sensitivity in Chicago of any of the major cities. Most studies find LA is a little more VOC sensitive, but a lot of VOC sensitivity, NOx limitation, NOx depression. In Chicago, downwind areas are more NOx sensitive. However, emission control programs in the last few decades have really focused on NOx emissions. And as a result, we've seen NOx emissions decrease by about 80% since 1990 from our 6 states. VOC emissions in that time have decreased about 60%, but they've been really stable for the last decade or so. Our VOC emissions are not really going down. So we're kind of at this point where thinking for future, there's more to be done with NOx emissions, but really it's probably maybe a little easier to get at VOC emissions at this point. Not easy, but maybe a little easier. There's also a lot of research out there recently that finds that there's a lot of previously underestimated sources of VOC emissions, like volatile chemical products, like cooking emissions. A lot of work out of NOAA on this topic. This is a figure from a recent paper by Kelsey Stockwell at NOAA, who estimated that in LA, VCPs in cooking are contributing about, combined about 8 to 9%, 9 ppb of ozone there. So that's a lot. And if we can control that, another question, separate question. But that's a big, that would be a lot. So another recent paper by Martina Rogers and Tim Bertram at UW-Madison, connected with Aegis Plus, that found that terpenes from VCPs were really disproportionately responsible for VOC sensitivity in Chicago. So that is in our area that we work with. So another just kind of line of evidence that we really need to understand VOC reactivity and emissions in Chicago if we want to reduce ozone in the area. And so we're currently putting a lot of work into this. Like I'm actually working, I think it's on the next slide, but I'm working a lot with some of the monitoring data. We're working and trying to understand VOC emissions, trying to understand, what control programs are possible, what could we possibly do. Just a note, obviously VOCs are important for SOA formation and also as air toxics in their own right. So basically, message is VOCs. And the question, of course, is how can satellites help? How can HAQAST help? Problem, VOCs are really hard to monitor. Generally takes a gas chromatograph or some kind of mass spectrometry to get at. Very expensive. As a result, there's not many monitors. This figure shows all the monitors, at least state-operated monitors, state EPA-operated monitors in our region that monitor anything. And some of these, like one of the monitors in Northwest Indiana, outside Chicago, monitors benzene only. I mean, it's great to have monitor benzene, but it doesn't, there's thousands of VOCs. Even the complete PAM suite, which is our most complete set that's monitored routinely, measures, at best 60 compounds, and maybe only 10 or so are not hydrocarbon, 10 or so carbonyls. So we're really very limited. I mentioned I'm working with PAM's data, which is very limited, but kind of the best we have on the ground. Of course, you can see where I'm going with this. Satellites are good at filling in gaps between monitoring. That's kind of where what could be really useful. However, right now we really only have formaldehyde that's routinely monitored by most satellites, which is really useful for a lot of things. Arlene was talking about some of the ways you can use it, but if we're trying to get at emissions, it's very non-specific. It's formed from primary emissions, it forms from secondary emissions, from reactions in the atmosphere. So it's of limited use for emissions estimates, but kind of my wish list, one wish list would be, could the temporal resolution available from Tempo help us sort out some of the sources of formaldehyde to make it more useful. So, different sources are going to have different temporal profiles. We know secondary formation is, peaks in the afternoon when photochemistry is happening. That's going to have a different temporal profile than primary emissions, which I'm actually not sure what they would look like for the different kind of time frame. And, the spatial resolution as well. So that's sort of one thing. I don't know exactly how, I could imagine some machine learning processes taking a lot of data, putting it together, but that's sort of one way that one approach would be to make the formaldehyde product more useful. Another is to use a different kind of satellite. And Arlene already kind of mentioned the CRISP satellite. Most of our applications currently work with UV-Vis radiation, which limits you to kind of formaldehyde, glycol, but there's not, most of the VOCs don't absorb in the thermal or in the UV-Vis range, but a lot of them do in the thermal IR range. And so there are some satellites that measure in that range, and that does open up a lot more potential of looking at a lot more VOCs. The cross-track infrared sounder CRISP is the primary one among those. And I think it's on actually 3 US satellites, and I ran across at least one paper on a Chinese satellite too. Been used for Japan and ammonia, and Dylan Malay's lab at Minnesota is, as far as I know, the only one that's doing a lot of work on VOCs with that, but there's some really nice work. The work I've seen published has been at pretty low spatial resolution. I don't think that's an inherent limitation of the instrument. I think that's sort of, they said, let's start with this kind of coarser resolution. I think you can go finer. I'm not sure. They've also relied on machine learning to get from the signal to, a guess of the emissions or the things. And that also just makes it harder for end users to do. So an ask here would be if we can expand the work with Chris and try to facilitate its use and application by end users, that'd be great. I only have a minute left, but I'll just say, last thing would be, we obviously do have needs for NOx emissions as well. And so there are some data sources that we don't understand, emission sources we don't understand as well, like freight. We're sure we're underestimating freight emissions, NOx emissions. Data centers, obviously a very, very hot topic and a rapidly changing one as well. And energy use, at and for. I think a lot of the energy use is probably intermittent and maybe not monitored by continuous monitoring. So with that, I will stop. And I think we'll do questions all together.
If our panelists could join us up here, that would be fantastic. And then we'll open the floor to questions. What questions do we have?
Oh, yeah, great presentation. Thank you. A question for Dan. So what kind of tempo data did you use as the input of machine learning data? And did you apply any bias correction for tempo data?
So for what I've done so far, I've not applied any bias correction, which obviously is a problem because I know with like the ozone retrieval, there's latitudinal biases. So the plan is that if it's a systematic bias that's uniform across the country, you don't really have to worry about bias correction because we're not really relating. There's no sort of chemical process that we're trying to relate. It's just those observations that we see from tempo to what we see at the surface. So as long as the bias is consistent, then that's fine. If it's varies by region, then that's something that we're going to have to do. I think we can use Pandora observations, comparisons to retrievals from OMI to do bias correction that way for the individual retrievals. I guess for specifics, I'm using the total column ozone, the tropospheric NO2, and the formaldehyde retrievals, as well as some of the viewing geometry things like solar zenith angle.
Okay, thank you.
I'll ask a question. I'll take that privilege. It's directed at our 2 representatives for air quality management. So if we're thinking about advances with tempo over what you were doing before, there was still kind of discussion of what we could do, maybe more than what we're doing. So I'm wondering if there are certain barriers to using tempo data, whether that's believing it at this point or accessibility or just a work stream process. How do you see using tempo more? What needs to happen for that to occur?
Okay. I guess I was talking with Tracy on the drive down here that I haven't actually tried really yet because it sort of hasn't been up to the top of my workload. Like I understand, and I know there's a lot. I'm actually taking the training tomorrow. I'm looking forward to that. I mean, my understanding is that I think there are a lot of trainings out there, and I think that, you know, if I had time, I would ways to do it. So I sort of think the limitations will be that on my time part. But I haven't looked deeply, so I can't really answer that. I haven't really tried.
Yeah, and I'm kind of in the same boat. We're in the process of dealing with retirements versus hiring new people in the near future. So there's a lot going on, but I think the biggest thing for us is just knowing when we have questions who to ask, and then from there kind of seeing what we're able to do at that point.
Do you have anything to add there?
Sure, why not?
Uh,
In fact, because of that, there was some ongoing discussion, I guess, at least between me and Westar, I guess, Mary, about what we want to do for sort of the training too, and kind of separate out the tiers of the users depending on their need. And one thing that we kind of agreed, I believe, is that at least the coding should be the last resort, so that we have a ready-to-use tool even before relying on any coding involved in. Because like you mentioned that a lot of state agency, this is part of their work, not really full-time. So that's the kind of way that I can see that we can have more users. And the other aspect of it is like data in an HAQAST, that you can just grab the data and start to your analysis, not without really thinking about whether this is the data that I have to revise later, because the data has been QA'd and curated already. So I'm kind of proponent, emphasizing that eventually I hope the research community come up with some sort of the recommended data sets, although there's a lot of other deep down research going on. But for sort of the regulatory users, we can rely on certain versions of data to conduct some analysis on their own for their reason. So.
Can I have one thing to that? I mean, I think one thing for me, just generally about using satellite data, is what I'm most worried about is the QA and like whether I can do the QA well. Because I know I can do it badly. I know I could just take data and I can do something with it. But I've basically relied on collaborations with researchers like Dan Goldberg and Brad Pierce and Gerald Dunn to do my real satellite work. Because in which case they take the data, they make sure it's really highly QA'd, and then I work with it. And so that's sort of something, I think it's something that I could use most help with, is like, how do you do it well? How do you make sure it's really high quality data? And also what I want is I want the data myself to be able to work, like I want the daily data to like, to choose, I want to look at these data together and do my own averaging. So, I'm a user, but that's sort of probably what I could use most help with, is like, how do you take it and how do you make sure you're actually using it for valid purposes.
Thanks for great presentations, you all. And, maybe just building on Byung's conversation, I think there's sort of a meta problem with satellite data for air quality management, which is that it isn't distributed through the EPA like the HAQAST data. And I think if it were, then they do the validation and it would be easier and it would be consistent, but we're not there. And so I think that like this issue comes up so much around ozone production, where on the one hand, I think the ratios and the tools have come to the point that they have been proven to be useful for air quality managers, really through the work of a lot of people in this room. On the other hand, then of course you have scientists and professionals who are like, but it's not the surface. It's been shown to have biases. It's not ready for prime time. Or even, science is competitive, and to be like, my data product is better than what other people are using. And on the one hand, that is a productive, positive cycle in the scientific community, but I think it runs into a lot of complications when trying to engage professionals and air quality managers. And I think one thing that I sometimes struggle with is that if we're not sharing the power of these data with the air quality management community, then first of all, that's a lot of gatekeeping. And second of all, then of course, there's never going to be better data if nobody's using what's currently available. On the other hand, then there's the counter argument to say, are we overly promoting it? Are we overly selling it? Are we trying to encourage something that's still in research mode to be used in applications mode? And I guess I'd be curious from the panelists or anybody else in the room about kind of how, whether overall, but especially in this ozone sensitivity space, can we be walking that path to make it easy and usable without overselling it, since it isn't AQS data?
I mean, I guess I can think, I mean, thinking about kind of what I said in the critical review on satellite data, is that I think it's a case of towards getting it useful for stakeholders, for the regulators. It's going to take time, and it's going to take education about what can and can't you tell here. And it's a similar process to what happened with like photochemical modeling. And I think it is just gradually putting it out there. I think you lobbied to get satellite NO2 in Wisconsin's air quality trends report. And we've been using like the Randall Martin surface estimates of PM 285, like LADCO's used those a few different places, kind of put it in front of the states, help them kind of understand what it is and isn't telling you. And I think it's sort of just a process of I think what HAQAST is doing, trying to put it out there, try to educate, get the regulators to understand too, and hopefully,
Yeah.
eventually I think we'll get there because it's so useful. I mean, like the surface estimates of PM 285 are amazingly useful with all the limitations, but
Thank you.
Oh, thank you guys for your presentations. I'm with the ASTC in NASA Langley, and I work with people who are very close with tempo data. So I guess this is for you guys and for everybody. If there are any sort of limitations, concerns that you guys have with tempo, satellite, anything, I'd be glad to connect with you guys. And we're always trying to make these data sets a lot easier to use and understand. So you can come to me and I could take some, I guess, concerns from y'all and bring it back.
Might just add on that. I think that, ultimately it seems like it should be in the user's court as to how useful a certain type of data is. And I think it's on, kind of the technical folks, the scientific community, whatever you want to do it to communicate what those uncertainties are. And, I feel like over the years with various conversations, listening sessions, et cetera, with different organizations, one thing that always comes up is, what are the uncertainties? What are the pitfalls? What am I likely to do that anybody who knows anything about this product is going to say, oh, wait, no, don't do that, And so I think that that's something that we just should be keeping front of mind as we explore the power or not of what these new data sets bring. And just keeping in mind that like having geostationary data for air quality is brand new. And so there's a lot that still needs to be learned, and what is the information we have? How does that vary with time of day? To what extent, well, I could go on, but I'll stop.
Hi, thanks for the presentations. So one of our PIs is working on some like ozone stuff for Chicago, and I don't know if any of you guys have any experience working with like super local versions of the tempo data, or like I know there were a lot of like regional plots that were in those presentations, but I don't know how localized those estimates can be, or if they should be used that locally, or if you guys have any experience with that. Let me take that one.
So if you're talking neighborhood scale, which I'm guessing is what you are thinking about, I would say that I think it right now, probably not, right? We're looking at pixels that I think can get you a nice urban to rural gradient, but probably not neighborhood scale. That said, with Trobomi, which is kind of the closest instrument that we've had to date to tempo, but it's a once a day overpass, there's been a lot of powerful downscale. I shouldn't even use the word downscaling really, but basically you can if you don't need like the hourly data or the daily data, if you can make a monthly mean work or an annual mean, then you can take advantage of the fact that the instrument, the way it samples, is viewing pixels slightly differently. And it's the technique is referred to as oversampling, and you get a higher spatial resolution than the native pixel resolution of the instrument. And so my understanding with tempo is that the same types of variations in the viewing angles happen, such that you could potentially take advantage of that. I think that raises a lot of really exciting questions, right? You could think about coarsening either in space or in time, and potentially once we have years of data, coming up with kind of climatological monthly patterns. I don't want to speak to what the spatial scale of it that's possible, because I really don't know. But I also think that that's where, right, some of the kinds of techniques that Dan was presenting with machine learning, if you do have some data on the ground, you could potentially downscale in different ways.
Thank you.
Thank you. Very wonderful presentations. I was a PhD student from UNC Public Health. I have a question for Dan about machine learning technicals. So I was also doing for the downscaling, also mapping stuffs. So I was dealing probably with monthly or yearly skills, but for the hourly skills, one question would be like, what the time scale you was doing the machine learning on? Is for 1 year or 1 month?
So, I mean, what I showed today is only, I trained the model on 2 months worth of data, so hourly data for 2 months. The plan is to train it, I mean, ideally using, from tempo launch till present. I think there's several limitations, and we're gonna have to, do a lot of work trying to figure out how we should subsample the data, whether we can use one model for everything. It will depend. So, but I mean, the plan is to use the hourly resolution data for as many months as possible, and potentially weighting the data set so that we're focused more on the high end of the range of ozone observations, so we can try to fix that underestimate problem that I was talking about.
Thank you for asking these questions. But the things you mentioned in your slides, you talk about maybe you cannot capture the extreme event in some case. So I think that's probably very important to choose the time range when you run your machine learning, like you only focus on 1 day patterns or the monthly patterns. So I'm not sure how you think about this if you want to look at the hourly data, which the extreme event will be important, or time scale you will choosing for run each bench of the machine learning is for 1 month or 1 day.
So I mean, the way that it's run right now is that it's all one model, all hours, all days. And so hour is an input to the model. So I think that captures some of that variability. I think that is one of the issues that we're having with the West Coast is I'm not really, it's all just looking at UTC time right now. And so it's just sort of focusing on the East Coast and just messing up with the West Coast. So I think if we, or add something as simple as a UTC offset, I'm hoping that will fix that sort of issue. So yeah, I mean, with other work that I've done, I've found better success with having separate monthly models. So maybe having separate hourly models would be better. I think one issue that I'd be concerned about breaking the model up into sort of separate times of day is I think that could lead to lots of weird discontinuities. So I'm not sure that would, I think that could solve maybe one of the problems, but then introduce another problem. So I think this is, I mean, why we're sort of starting from the ground up here. So we're interested in looking at multiple different machine learning approaches as well to try to see the best way forward for this.
Thank you.
Can I ask a question? Yeah, since I have the microphone. So you were talking about the traffic controls in New York City that you hadn't really seen a signal. Has there been any on the ground data that would help indicate whether you would actually expect to see a signal?
Yeah, we have not looked at on the ground data yet. We were mostly looking at a satellite perspective, but that is something that we could investigate, and maybe that will tell us something.
We have a question over here.
Talat Otman, Georgia Tech. So I thought the cases that Arlene has shown, the smoke cases, were interesting. High PM with low ozone and lower smoke with higher ozone. I mean, my guess is, smoke is so dense that it's suppressing photochemistry. But looking at the list of predictors that Dan has shared, I did not see any connection to PM 2.5. Maybe I missed it. But anyway, my question is, has any of you used AOD from Tempo, and where does that stand? What is your experience with its accuracy?
So I've been working with Amy Huff before the government shut down, looking at some experimental data for AOD, aerosol layer height, surface level PM 2.5. And it is very interesting to see different, I want to say, like, it's interesting when you can see a case where there is smoke aloft that's not impacting the surface. The problem I have had looking at that data, unfortunately, is all of the test data either is a day where it's too cloudy for something that I'm interested in looking at, or because it is test data, they weren't running something for whatever day, or tempo was down. I think it was the beginning of August. There were some interesting events and tempo data wasn't available. So for me, I feel like I haven't been able to actually see a really cool event and then be able to analyze that. Because even for the 2023 smoke events, it was too early. Tempo wasn't launched. So, or the data wasn't available. So for us, it's just we don't have enough days or enough hours or enough events to look at. Maybe we'll have an hour or two before the clouds moved in to see something. So that's just my perspective on it.
So I was just going to say I'm a little hesitant because this is really brand new work, but my student, Joe Palmo, because of the issue that Amanda said, so we have like airborne data and Joe's pulling what he can out of the observations and doing some really nice work. And like, hopefully he'll be at the Wisconsin meeting in the spring. But one of the things that we stumbled upon and are super excited about right now is that Siwen Wang, who is at University of, oh gosh, now I'm afraid I'm going to get it wrong. I think he's at University of Miami in Florida. But he has a beautiful paper doing some fire chemistry analysis in WRF LES with chemistry. And so it gives you this amazing test bed if you want to test a machine learning model or a simple steady state model, for example, for ozone production in a wildfire plume. And so I'll just say that I feel like there's more we can do as a community of bringing together observations and just a whole range of different kinds of models. But ideally, you want to convince yourself that your tool at least works in the idealized case where you have all of the information, all of the reaction rates that you could want. And if it doesn't work there, well then, you know, when we get to the complicated real world observations, it's probably not going to work. So just sort of a shout out to Siwan Wang for sharing this data set. And I'm sure that if there are other applications of it that he would probably, I don't want to speak for him, but be delighted to see it used. And while I'm speaking, can I ask a question? So Talat, you kind of set me up because I was sitting here thinking about, you know, from the regulatory perspective, our air managers, right? You kind of end up having to focus separately on ozone, separately on PM because it's a completely different process. I mean, sort of, it's different processes, different standards. And so I'm like thinking I was in the compound event this morning and do you track at all whether there's like how often co-occurrence of PM and ozone or heat and ozone, heat PM and ozone are happening? It's something that at some point I had an undergraduate starting to work on, and it's been in the back of my mind for a while. And this discussion is kind of making me wonder if you all actually have all this data about co-occurring pollution and or heat.
Not exact. Yeah, not exactly. I mean, we don't exactly track that. We do. I mean, we have been thinking a lot about PM in the last few years and about a lot about ozone, and so we do kind of notice that. So it's kind of informally, and I have, you know, set up trackers for which days have we think have smoke impacted, you know, PM and then ozone and all that. So it's like, it's not like pulled together like that. I feel like it would not be that hard to do that. But I haven't, not exactly.
Love to talk.
Yes, yeah. I actually respond to the earlier question, but you.
Okay. So in Connecticut, there has been some discussions about potentially doing exceptional events for the greater Connecticut area. We do believe that because of the presence of wildfire smoke, that increased our ozone design values. It was 73 this year, 2024, I think it was 72. And also, interestingly, while Groton did reach 73 parts per billion for the design value, East Hartford did as well. And typically, we don't see that. Typically, we see Groton being that main site that's showing that highest ozone design value, and everywhere else is lower. So we did do a little bit of looking into things, but again, not in like a here's a spreadsheet of the data. But for the past 3 years, we did see that out of our 22, I think it was 21 at the time because it was before the October 5th exceedance. We did see 14 of our days for 2025 showing at least some type of a presence of wildfire smoke. We have also found that sometimes even just having a little bit of light smoke can make a huge difference. Like somebody mentioned, like when you have too much smoke in the atmosphere, that I don't know if the sunlight just can't reach those NO2 sources to help form that ozone, but we do, those events that Arlene was showing are very interesting to see why didn't we get those ozone levels. And that's something we briefly looked at, but did not look significantly in depth at.
Let me actually revise my answer. Let me revise my answer a little bit. Because we actually do, in the sense for exceptional events, Single Nurgui, one of my colleagues, she does actually have a tracker. She updates monthly to try to look at, like, engage whether we might have a potential ozone exceptional event. And that pulls together monitor ozone, monitor PM2.5, and monitor carbon monoxide. And it kind of looks at and with a threshold of over 1.5 standard deviation over the monthly mean. And so that's kind of, so she has like kind of every month we meet with our states and kind of say, oh yeah, it looks like these days, you know, so that does pull them together in that sense. So yeah. And actually to the, back to the question about AOD, Gerald Octon, who just defended his dissertation at UW-Madison, Brad Pierce, he has his dissertation was really focused on wildfires and ozone in the Midwest and, you know, Great Lakes area, like Michigan particularly. And he has a really nice figure that I've used several times, looking at, and it's model-based. I don't remember if it's all model-based. It's model-based AOD. I'm not sure, or if it was satellite AOD, but basically finding the additional ozone you get compared to additional PM2.5 you get separated by AOD. And you basically see if you see really high AOD, you know, you get more less ozone, and you know, but he sees a really big impact of shading from the aerosols, and which has actually made so much sense to me because I'd been puzzled, like actually those, not exactly those episodes, but we had in 2023 we had days when it was really smoky and there was no ozone. And days when it was really smoky and we got ozone. It was like, what the heck? But it was, I think, just that the smoke was really low and didn't extend upwards. But I need to Gerald's dissertation for sure.
If I could ask you the exact same question about Atlanta and our fire ozone relationships. Yeah, you're really like the answer.
Yeah, I mean, so I think the reason that outside of the air agency, people think that the air agency may deal with pollutant by pollutant. That's just because the requirement by the Clean Air Act that we have to deal with each criteria pollutant through their own SIP. I guess a SIP is more bigger umbrella, but each pollutant need to be addressed. But under the hood, agencies are not necessarily tracking, but dealing with the multiple pollutant at the same time, depending on the sources. In fact, in Georgia, back in like a 2010 timeframe, that we developed the Georgia multi-pollutant rule that regulating the power plant that is targeting the ozone and the PM2.5 and the regional haze at the same time. So that's one example. And going from there to now, that we are also, like other agencies mentioning, that we are looking into the days that are affected by fires for PM2.5 as well as for the ozone at the same time. So, I mean, so basically air agencies are looking into multiple pollutant at the same time for each pollutant.
Thank you. So with the comments on multiple pollutants and multiple stressors, I think this is a good time to note that one initiative that NASA, NOAA, and EPA are moving forward with is a website called Air4US. And this is something that NASA has asked HAQAST in particular to play a role in helping get out there. And I guess I'm curious from all of the panel's perspective, like what is a application area where having data from multiple agencies together could fill a gap that isn't being filled by current. If you could have like one wish list item for the Air4US, either what's on it or the application of it, what do we need?
I have a wish list. Let's call it as my dream. On and up, I mentioned that for air agency, we have to deal with the permitting program and everything, and eventually we want to have the data set nicely, I guess, prepared in the form of the next. That being said, annual PM2.5, a lot of people worked on it, but I have not seen really much about PM2.5, which is 98th percentile and 3 years average, and all those complicated statistical calculation. And same as ozone. I mean, Donald profile and the monthly average is also great, but at the end of the day, it's a design value that's going to be the critical information. So keep it, if you can, please keep that in mind, that data set will be very useful for air agencies in a ready-to-use form, like off-the-shelf tool. And the other thing is, you keep hearing about the exceptional event. So when you develop the product, if you can develop like second set without wildfire impact for somehow, then that can be very useful. One prime example that I can share with you is that the modeled data set that developed by the EPA by Dr. Heather Simon, that she ran the CMAQ twice, one without Canadian fire and one including Canadian fire, so that you can subtract it to see the impact of the Canadian wildfire at each monitor location. That's pretty handy. So that's my wish list / dream. So
Okay, love it. Thank you.
Can I add to the wish list here? So I was thinking, actually, I am often searching for information with respect to teaching, or like kind of building hypotheses or thinking about, wait, do we know this? Do we not know this? Somebody probably knows this. How do I get this information quickly? And one of the things that I find not so easy, and this may just be my own like lack of being in the trenches and doing a lot of this work myself anymore, but is just getting a plot of emissions. And so could we have the NEI emissions, not just the current version, but like going back in time, or like the whatever harmonized sort of thing was done to go into like the EPA equates modeling. Personally, I think having that alongside the actual air quality measurements, and while I'm adding to my wish list, can it also be like the PAM sites and all the extra data that goes along with that? And can we just easily get it all in the same format on a map, or download it? Can we download PNGs to put in slides for class? So there's, yeah, I could keep going, but I'll stop.
Some of your dream actually fulfilled by the ASDC, because they publish the L3 data through the ArcGIS Pro, the ArcGIS Online. So
Okay.
that might be a good example. Sorry.
Great.
Yeah, I'm thinking also, if there's ways to choose days to combine averaging or whatever, that'd be something that'd be really nice. Because right now it's basically like, I can take all of March, or I can take a whole year, or I can take this particular day. And I'm like, well, I want to be able to choose like all the days that at ozone over 70 or over 80, or, you know, like to do my own averaging. You know, like a single day isn't that useful because there's clouds and there's, you know, but like some kind of like choose your own adventure averaging would be really useful, of like multiple parameters.
Arlene kind of touched on what I was thinking, which is more uniform data formatting and easy to use data formatting. I've recently started using EPA data. That's not something that I have much experience with, and I find it incredibly infuriating. I mean, there's Excel spreadsheets that I'm using that I can't open using Excel because they're so giant, and I have to use MATLAB, which doesn't seem like the easiest way to access that data. And I mean, I know NetCDF and HDF formatting, I assume, which I prefer. I assume most people don't prefer that. So having some sort of more easy to use data, I feel like even from a scientist perspective would be nice. So I can imagine if you're not a data scientist.
I see a lot of nodding on that topic. So I think we reached consensus. Let's thank some panelists again.